3, 2,
Which one?
there you go.
All right. Twisty.
Yeah, it's just this thing again. Yeah.
There we go.
There you go.
All right, check. Hello. Welcome to DroidCon 2024. My name is Tim Hebel, which you may or may not know. Yay! So today we're going to talk about design considerations for 3D printing. To be clear, this is not how to use Fusion or how to use any other tool. This is a tool agnostic. Although I do use Fusion, and I can talk your ear off about my tools, techniques, and bad form. This is mostly when you're building it, what I think about when I go to design any piece. So here we go. So this is what we all love to do, and take what's in your brain and put it into reality. So we're going to talk about make it printable, make it buildable, make it maintainable. Because anytime something breaks and you're at a con, you don't want to do the walk of shame. So that all starts when you start building the part and design the part. Before it ever gets to the con floor, we've done our homework and created something that's going to be reliable. So pay attention to the fine print. Print, get it? No, all right. So we're going to talk about part thickness, strength that is in the walls, multiple part assembled will be stronger, fillets and chamfers, print orientation, integrated supports, clearances, nozzle sizes, bed sizes. So these are kind of like the overarching framework that I lay my design pictures on. And we'll go into each one of these in a little bit more detail. So part thickness. In general, we're dealing with plastic printed stuff versus resin. I'm a fused deposition modeling guy, FDM. So you squirt the plane, it sticks together in multiple layers and creates a part. So how thick does that part need to be to do the job we're asking it to do? So if I want something cosmetic like this holo projector, these walls here, they're 3 millimeters thick each. And smaller than that, I can get away with, but then I'm going to lose, like it may break while I'm sanding or painting it. So 3 millimeters is generally thick enough to do light duty work, maintain the shape. Now, obviously, you're going to have to go smaller and thicker depending on the use case, but as a minimum, I'm going to start with a 3 millimeters in general for small parts. When I get to medium parts, like Arduo or Ardivo's radar eye here, it's got a little work to do. It's going to hold some electronics. It's going to hold a piece of glass. So it's going to have some structural work to do, but not a lot. It's not load bearing. It's mostly cosmetic, but there's work being done. So 5 millimeters thick is how I started with the wall sizes. If I'd gone with 3 with that, you might be crushing it or breaking it if you take the part on and off or whatever. And then when I get to actual structures, for example, the dome or the body, 8 to 10 millimeters will generally be thick enough with reinforcements and other techniques to give you a structure that you can handle. Now, if I'm building a leg, it's going to be much thicker. Like you're just, if you can imagine, the size of the piece and the thickness of the piece is kind of dependent on the work we're asking it to do. And for example, on Arduo's head rails, people tend to, I pick them up with the rails. I put them over and work on them on these rails. So that's actually got some structure to it. And that's why the pieces are as thick as they are. And just coincidentally, cosmetically, that's the size they look like they were on screen. So when you're thinking about 3D printing, the strength is in the walls and somewhat the infill. So when I'm thinking about printing, and I'll talk about nozzle sizes a little bit later on, but most nozzles are 0.4 millimeters thick. So if I'm printing a leg for R2D2, I want 6 walls and I want 30 to 35% infill. You say, why not go 100% infill? Because now you're wasting plastic. There's a diminishing returns because the space between those walls is like like a lever or a fulcrum. The farther apart they are, the more torque and whatnot. So you don't want all walls. You want some interaction between those two. And the point of putting too much infill, you're just going to create stress lines that would otherwise be hidden in the infill. So if I'm doing a 0.6 nozzle, you can get away with the same thickness of wall, but now you need less passes because your walls are thicker by the fact the nozzle's thicker. So you might do 4 walls and like a 30 or 25% infill and get the same strength out of that piece. Multiple parts will be stronger when you put them together. So this is a cutaway of our Duo's base plate. So I see I got a 10 millimeter base. Hey, where'd he go? I guess it's taking a break. We'll give it a second to rethink its life. But we can plug. Oh, we're back. All right, so the base plate for a skirt is 10 millimeters, and the base for the body is 10 millimeters. When I stack those two together, I get, if I had just a 20 millimeter piece, I'd get 3 tops, 3 bottoms, and 20 millimeters of infill. But when I take that same dimension and put 2 pieces there, now I get 3 top, 3 bottom, 3 top, 3 bottom, and the same infill. But now they reinforce each other. Think of it as if you took a stack of index cards. You can rip one easily, but if you get 10 or 12 of them, they don't rip, even though they're the same thickness each. So stacking helps. And it also helps with print times and assemblability. And so I don't always want to put everything together, but if I need strength and I'm working in plastic, stacking or laminating or layering really can add a lot of rigidity and structure to your builds by simply taking the same space you have and putting in different parts, because now the layers will cross each other. As you know, so you get a lot of advantages by simply stacking the pieces. Fillets and chamfers. Don't forget these, because layer adhesion is all about how much surface area those pieces have when you're bonding, when the plastic's cooling. So if you have less surface area, you have less adhesion. And remember, any print is only 1 layer thickness strong. It's going to split at a layer seam, and we'll talk more about that in a little bit. But in general, if I'm putting a hole into something that I'm going to put a screw in later, we all know that the hole sizes tend to vary depending on our printers and whatnot. But if I put a little chamfer around the edge of that hole, 0.5 millimeters, even 0.25 millimeters, it gives the printer the cue that this really needs to be a hole, particularly when you get smaller and smaller holes, as hole sizes. Putting a little chamfer around the edge will really help you start those screws and or find the hole if you're like doing a servo mount where the hole is only 1.2 millimeters to begin with. That can sometimes get lost in that top surface unless you put a little extra, not over the whole hole, just the entrance of it. And then fillets, curvy things are naturally stronger. When you get to these sharp edges here, there's a lot of reasons not to have sharp edges in your parts. First off, when you put it on the print bed, a sharp edge is going to radiate more heat around the edge and just want to curl up. But if it's a round edge, it doesn't have that single fulcrum point to jam the heat out and cause as much thermal cooling as the part is getting printed. So I avoid square shapes on print beds always if I can. Sometimes you can't because it's part of the nature of the piece. But for example, this thin and long is the devil when it comes to printing, because those thin, long pieces don't cool evenly and they tend to warp, particularly if you're printing in a drafty area or whatever. So as much as you can, curve those things off and add fillets for strength, because that gives us a broader base. So that one line of that one line layer snap is likely to happen because I've got more plastic, more structure to spread that load over. Does that make sense to everybody? All right. So print orientation is paramount. You have to think, how is this part going to exist on the print bed? So here we have a mock-up, excuse me, of a layer line, of layer lines on a print, and I've got myself a nice chamfer, and you can see as I go up, I've got more plastic to hold on and do the work. So if my stress on the part that I'm going to use is perpendicular to the layer lines, just think of it, you're splitting right down and it's going to crack right open. But if my stress is with the layer lines, that's good. So I want to have a print orientation, particularly for structural parts, where the stress I'm expecting on that piece is going to interact perpendicular to the layer lines. So I want to have it print so that those layer lines are going to help me in the long run. If I printed this part on its side and the stress was coming at it, you can expect that part to crack and fail on you. So it's a little bit of print slicing philosophy, but that goes all the way back to the design philosophy, because in general, when I release a part, I orient it for the print bed that I'm expecting you to use when you print it. Also, for just cosmetic reasons, so here's these pieces right here, these little bezels that go around his logic lights. If you look at the actual piece, it's got a 40 or 30 degree cut here, and it rests on the bed at an angle. So when I print these lines, these curves, they're not layer lines, because you could easily throw that part on its back and you get the stair-stepping, this effect on the top of your print that you have to sand out. But if I print it this way, there are zero stair steps because the printer can draw a curve like that. So when I went to design this piece, my first cut was lay it on its back, and I had all these little stair steps. The piece didn't fit because I messed up one of my clearances. And when I went back for a second pass, I'm like, you know what? I didn't like having to, and plus I had an event. I didn't want to sand it. I wanted a clean plastic look. So I reprinted it with the printer doing the hard work of making that nice curve. So there's many different things you want to think about when you build the part, and make sure that your print orientation is always top of mind. Integrated supports. Modern slicers have gone a long way in creating great supports that break away nicely and generally will allow you to print weird shapes. However, as a designer, if I can, I'm not going to have you use any supports that the printer or the slicer generates, because those are not optimized for the design I just made, for strength, for cosmetic reasons, for all kinds of things. So here's a perfect example. This is a single print dome that you can print without supports. And if you look at it, the exterior has places that will obviously need supports. These flat edges can't print it floating in space. So what I did was I created like a bell shape on the interior, so you can create a bell and it will support itself as it goes up. And at the top, you're going to get some sloppiness in there, but it's on the inside, it's cosmetic, or it's not even cosmetic because nobody can see it. And it's not structural because I've got enough plastic to support and create a nice solid top of the dome. These chamfers here, were blown out so that it's not trying to create a hole that needs, this area right here is unsupported. But if I'm building an arch, arches are naturally or an arc are naturally self-supporting. And if I gradually go out a little bit as I grow that arc, you can print this without support. However, right here, you can bridge surprisingly, 30, 40 millimeters, depending on your printer and your plastic and those types of things. But when you want a nice clean line, this has to have supports here. There's no way to defend that without supports. So there's two ways of handling that. One, I can, as a designer, go enable supports and hope you get it right. Or two, I can build a thin wall that is a support, but it's part of the model that I intend for you to break away after you build it. So like sacrificial walls are perfect if I have a surface that goes up like this and there's a hole in the top that I'm putting a screw in. So it's gonna like kind of fail unless if I put just one layer, 0.2 millimeters at the bottom of that hole, you can poke your screw or drill through that easily. And now that hole's perfectly living in space, and I've just got a wall that gets blown away when you put the model together. So generally 45 degrees of an angle is the perfect one. Most printers can do that easily. As you get lower and lower angles, it gets more and more horizontal and less likely to work. But even those, you can get away with certain amounts, like you can get away with 1 millimeter of just straight out, which may not sound like a lot, but sometimes if you're building little cut lines like this in your droid, you have your lines that define the panels, you can jut out 1 millimeter and not have that supported. But even those, I'll generally sneak in a little chamfer underneath those so that I don't have to go all the way out 1 millimeter and I get a cleaner line. And generally you can do circles, like I said, without supports, but the top's gonna have a little droop in it that you'll have to file away. Clearances. You can't take a 40 millimeter buck and fit into a 40 millimeter hole. It needs to be a little smaller. How much smaller depends on what you're trying to do. If you want two pieces next to each other, you have to have at least 0.2 millimeters clearance, even though there is no clearance in the real world. Those are right next to each other. But the surface of the plastic's not smooth. Even if it looks smooth, but it's got little jaggies that when you take two pieces that are going to butt up against each other, you need to slice 0.1 millimeters off of each side of those so that when you put them together, there isn't a gap. Or like if I was putting a dome together in pieces, if I did that, it wouldn't fit all together because there's just those imperfections are accumulative and add up. One of the things I didn't talk about in my previous slide with chamfers, but it's not on this slide, but I just thought of it. So if I'm building two pieces that fit together and it ultimately will be a smooth surface, one thing I do is I run a 0.25 millimeter chamfer on each of those surfaces to create a little valley in between those. So when I put the filler in it, it has some place to go. If I don't put a valley, that seam will almost never get fully erased. It'll be visible because just the pieces will move over thermal expansion. And so I got to give it a place for the filler to make that smooth transition to exist. So just make one as a designer. For snug fit, in general, I have a 0.5 millimeter clearance all the way around, 0.25 on each side of it. So the total gap is 0.5, not 0.5 on each side. And I use those clearances on pieces like this where they just fit in and it looks like it's exactly the same, but if you use 0.2, you're never going to get that piece in there. And you use more than 0.5, 0.6, 0.7, it's going to be loose. So this is all dependent on your nozzle size and your printer tolerances, but that's what I shoot for most of the designs. And if I want a moving part where I want clearance so that it rotates, if you're doing something that's doing work, add a bearing, add something mechanical made of metal that rolls so that that part won't wear out. If it's something that's mostly cosmetic and not doing any real work, for example, these hollow projectors, they don't have any bearings in them, but I did put in moleskin, which is like a little fuzzy cloth, so it can ride on in here, and that actually acts as a bearing or as a smooth surface to bear the load and keep those parts aligned while it's moving. And when I add a bearing, I use my snug fit clearance thought process so that bearing fits perfectly in there. There's no play, and it doesn't want to wander away. Nozzle size, I mentioned it earlier. So most people have a printer with a 0.4 millimeter nozzle. That's kind of like the ubiquitous industry. It went to 0.4 millimeters a decade ago, but slowly we've been seeing 0.6 millimeter nozzles and 0.8 and just bigger and bigger nozzles. My personal preference is 0.4 is good for small detail. If I'm building something structural, I want 0.6 because it's going to give me more strength. With a 0.6 nozzle, I'm going to have a wider bead of plastic coming out. to another wider bead of plastic. So there's more surface area for that bonding to occur and the strength to work. So I keep the nozzle size in mind when I'm building something, because a smaller nozzle will require less clearances than a bigger nozzle. Because when I'm printing something, you can think of the nozzle as a circle. And when the slicer goes to draw that hole in your thing, it's drawing with a big fat Sharpie. The center of that Sharpie is the hole you're trying to cut. And so part of the Sharpie's on the inside of your hole and part of it's on the outside. So your actual hole is smaller because how the slicers work, the geometry. Now, they do have slicers with the Arachne tool path technology, which will vary the width and the pressure to make your clearances and your accuracy more true. However, again, that's your slicer settings, and that kind of gets how you slice it. Slicing is an art form. But as in the design aesthetic, I changed the hole sizes I'm using based on what nozzle size I expect you to print that with, so you don't have clearance issues when you're trying to put the M3 or M4 bolt into a hole. Because I hate when you're like trying to put something together and the hole's not big enough, so you got to drill it out. I try to head that stuff off at the pass by doing proper clearances. In general, when I put my instructions out, I say, this is printed on a 0.4 or 0.6 nozzle. Particularly the bigger pieces, I generally do 0.6 nozzle clearances in mind. Bed size. Here's a myth I wanted to dispel. You don't cut a piece that's made for a big and just cut it into smaller pieces and start printing it. You have to re-engineer the piece for the smaller bed size. So here's our Duo single print. You can see I've got integrated attach points that will print without supports all the way up and down. And this is a thing of beauty. This was another week's of work to take that exact same shape and make it something that you can single print, because now I have to put it together. Now I have to add all of my little valleys for the joints so you can finish the thing off. And then I have to figure out how I'm going to attach this to that. And this one I use the little joints that are slightly off at an angle into heat insets. And I got to figure out where can I fit all those. I got to worry about the wall thicknesses, about the structure. And this is a whole nother problem to solve. So when people say, hey, can you cut this for us? It's literally a whole different job. And happy to do it, but it takes time. It takes time. So if you're designing something that's, keep the bed size in mind. Most printers can do 250 by 250 millimeters cube. That's kind of the old Prusa i3, Ender 3 standard. Bigger printers are coming out. And when we get to a world where everybody has a 300 millimeter or 500 millimeter bed, we won't have to worry about this as much. But particularly when you're doing one-to-one scale droids, keep your bed size in mind so that you can see that I've got these dovetail joints in here, and I can get away with those kind of face-to-face joints. The dovetail is really just to align it so that they fit together. It's not necessarily for structural integrity. But if you remember from the earlier picture on this, I know underneath that is going to be a sandwich layer. So even if that part is not super firm in this direction because of that joint, I've got an underlying joint, and the underlying joint does not line up. None of the joints line up. They're all spaced so that the joint on the bottom piece is not there, it's here. So again, stacking gives you that structural integrity, even with the 10 millimeters of plastic. Wrong franchise. So order of assembly. You got to keep that in mind too. I've built stuff, designed stuff, printed it, beautiful, but I couldn't put this into that. Perfect example is this little piece right here. It's a little stack with the electronics in it, the little atomic symbol, a diffuser, a lens keeper, and it all kind of sandwiches into a little disc, and then I slide it in the back underneath the magnet holders that hold this on. Except the magnet holders, and the geometry didn't work. I could not physically assemble it. So back to the drawing board, and if I were smart and could have imagined how this piece would rotate and go into there, and see that, oh, that would never fit. Sometimes you don't know that until it print it. I'm just not smart enough to figure out how to do all those clearances. But the first time that happens to you, you'll like, oh, I got to remember how this goes together. And in your mind, where's the screwdriver going to go? Where the like, you can't get a tool in there, even though it's physically accessible. If you don't, so sometimes you have to add little assembly holes, not necessarily in this piece, but in your design, so you can get tools in there to put the thing together. I try to use common hardware. If I can get away with 20 millimeter M3 screws for the whole assembly, I try to do that. But sometimes you need 25 millimeters, sometimes you need 10. So try to limit your parts. It makes it easier on the buyer, it makes it easier on the assembler, and it makes it harder on you as the designer, because sometimes you have to make some part thicker so that the screw's not too long to poke out the other side. And then, and this is one of my weak areas, is bill of materials. They say, hey, Tim, what bolt goes in here? I'm like, I don't know, because when I put it together, I just grabbed something from the bench stock. It was too long. I picked a shorter one, and I just put it together. I've mitigated this a little bit by making videos as I put it together and try to mention the hardware. Other times I will, lay it out and it'll be clear. I put it together, or I make a table and tell you what screws if I'm doing written instructions. But how you put it together is something that if I threw a puzzle on the table and it was upside down, you wouldn't have any idea. Like, all these pieces we know go into that puzzle, but if you can't see the picture, you can't put that puzzle together. Or you can, but it's going to take you a long time, a lot of trial and error. So try to keep that in mind as you put your instructions, and try to foresee where the trouble is going to be in this assembly in your instructions, and highlight areas. Because often I'll put something together that I design and like, oh, that's going to be trouble if you do this out of order, if you do something wrong. So try to capture those in your assembly instructions. Make your builds maintainable. It's not going to go together once. It's going to go together once when you make it, and you have to take it apart when something breaks in it, or someone breaks it for you. So I don't like glue. I don't like adhesive. Sometimes you have to glue things on, but if you can get away, use mechanical connections, screws, things that slot together and twist, whatever. Make it so you can take it apart and put it back together, because that gives you a lot of advantages in maintenance and future upgrades / changing things, because you haven't glued something in to the point where you have to destroy it to get it apart. And particularly when I'm iterating on something, it's nice to not have any glue involved, because I don't like glue. I was going to make it's sand sticky reference, but that doesn't fit here. Magnets. Use magnets wherever you can, because magnets make your life easier. We talk about the assembly and access to stuff. Having this panel magnet on solves so many issues. Just be careful. Don't use it on something necessarily weight-bearing, or it's going to have a lot of force on it. And if you are doing that, make sure you have some way to keep that shear, like my magnetic dome attachments, have shear studs in there with a bolt in it, so that's going to translate that torque around the dome, and because you can upset a magnet by giving it a 90-degree shear force, and it'll put right off. In fact, that's how you get strong magnets. You go sideways. I try to limit my tools. Magnets help me try to limit tools, but yes, prolonged activity. So that helps when you have common hardware, but just try to limit the number of tool sizes necessary to put together, if you can, if it makes sense to. Obviously, don't make any choices that is going to ruin your design, but that's something else I think of. And easy access to critical components. I just went from the bottom of the slide up. Did anybody notice that? So for example, my Arduino build in the back, he's got magneted on foot shells. So I can go boop, boop, just like a NASCAR racer, pull the foot shells off, lay them on his back, and there's a hole in my drive design that I could tighten up the drive gear if necessary. No, I mean, aside from the tool I'm tightening with, no tools to get access to the critical component of the drive gear. And if I do need to get access to the drive gear, say my Sonic hub is loose or whatever, and I need to tighten it, 4 screws hold on that panel, boop, and I'm at the drive itself. In fact, I can change his entire drive, and I have, when I re-wheeled him after MegaCon, and he was just sitting on 2 legs, and the other one was just, I could do all the maintenance right there on Droid without taking the foot off. So that's kind of a magic trick, but it wasn't because I designed it that way. So think of maintainability. It'll really save you a lot of headache and heartache a year from now as your design goes forward. So in conclusion, make it printable, make it buildable, make it maintainable. That's my YouTube QR code if anybody's interested, and I'm open for questions. Yes.
So I tried printing in 6 and 8 millimeter nozzles for strength and speed and the bigger stuff. But I found the lack of detail was a bit of a trade-off. So I eventually just decided for everything, I'll just print slower. You know.
Well, that's a good concept, but if you tried the Arachne slicing setting in your slicer, well, Cura has that. In fact, I think they were the first to implement it. So Arachne, just like the spider, what it does is that your nozzles, typically your nozzle is, your stream of plastic is 50% bigger than your nozzle size. So if you're printing in 0.4 millimeters, you're throwing out 0.6 millimeter traces. And they realized that if I back off my pressure a little bit, I can print a 0.4 or 0.3 millimeter trace just as precisely by not overpressurizing that nozzle. And I can also increase the pressure to create an even wider path. So with the Arachne slicer setting, you can take a 0.6 nozzle and get 0.4 clarity, almost like indiscernible. Yeah, so my favorite nozzle size, 0.6, because I can push out more plastic, I'm stronger overall, and I can maintain that detail with the Arachne slicer setting. Interestingly enough, that setting is not defaulted in the Bamboo printers. I learned that when I was printing this bezel right here. Actually, this one right here. I printed the first one just stock, and I had to clean out all the holes with the 2 millimeter drill bit. And then as I was checking the slicing setter, the advanced slicer settings, it said default, and I went Arachne. I turned it on, and this one printed perfectly with no, and these are really, really thin traces. Usually this is done on a laser cutter or like a resin printer, and you can get FDM quality out of it using an Arachne slicer or a smaller nozzle. You can put a 0.2 nozzle on there and get amazing detail.
Does the Arachne setting focus on holes or just overall?
Thin walls. It's a thin wall setting. Okay. So as you get, particularly, like I said, this is a perfect example. I can bring the slide up. So for people in the back, this piece here, these are 2 millimeter holes with less than a millimeter of space in between. And you can just imagine spewing plastic out and it's getting all sloppy and not going where you want it. The Arachne slicer can negotiate these super thin walls and not spew too much plastic out and corrupt the hole. So in general, though, if I put a 3.4 millimeter hole for a 3 millimeter bolt, the Arachne slicer is going to produce that 3.4 millimeter hole for me. So it's going to create the hole I was expecting, more or less.
So those rear lockers that you have on the store here,
Yeah.
printed on a 6 nozzle.
No, these were printed on a 0.4 nozzle on the Bamboo using the Arachne slicer. This dome was printed with a 0.6 nozzle. This was printed 0.6. So anytime I have anything bigger than this, I'm going 0.6. And even this, this was printed, one of these was printed on a 0.5 nozzle on my Sidekick, my low spot Sidekick, which is basically a Prusa clone. And with the Arachne slicer, these little ridges, they came out perfect. The first time I tried to print one of these back in the day using a 0.4 nozzle without thin wall knowledge in the slicer, these came out blank because the slicer couldn't resolve that, and it just, there's nothing there. It just disappeared, and I had to go in and enable thin wall back in Simplify 3D. But nowadays, with thin wall detection in the Arachne slicer, kind of defaulted in Prusa slicer, available in Cura, and hidden in Bamboo Labs, that setting will make these details pop and be available to you.
You didn't touch upon this in your presentation, maybe that is filthy, you might know. I've often wanted to put holes in STL that don't have a hole in electronics, and like, let's say you got a robot head, it's maybe like built. You know the way to put like a chamber in there and put a door on it. I haven't really found a good way if you just got the STL.
So if you just have the STL, I know for a fact Prusa Slicer does it, and therefore Bamboo does it because it's based on Prusa Slicer, and I'm pretty sure Cura does it. You can have volumes that the slicer generates, and then you can subtract from an STL, and it'll create the geometry for you. So you can poke holes in things with your slicer. I haven't done it because I have a CAD program, but in general, the way I would attack that is I would import that STL into my CAD software, convert it to a solid body, modify it, and then export it as an STL again.
Depending on how complicated the model is, sometimes doing it as well.
But you can also cut it or tessellate it in the CAD software to make it less complicated, and then put it back together. So there's ways to wicker that problem, but whoa, hey. At the end of the day, you can use a slicer, and like I said, it seems like you'd have to go in there and use a bunch of different views, but you can definitely poke holes with slicers. Yeah, so like there's workflows for that when you're trying to modify somebody else's stuff.
Are you doing step and STL? Are you a step man?
Well, what a step file is and an STL, so they're two different things. A step file is more like the Word document that you can edit. STL is more like a PDF that you can't edit. So slicers nowadays will eat both of them, but one of them you can open in CAD and rearrange, and like you can full up edit a step file in any CAD software, whereas that STL is more of an enigma, because what a step file is a bunch of triangles that are floating in space in a particular geometry with nothing inside. It's not a solid body. It's a bunch of thin triangles, infinitely thin triangles that form a shape. And so when you cut them, you now have a hole in your model that you need to fill with another thin series of triangles to make the shape you're expecting. Whereas a step file is working in solid bodies. When I cut that solid body, it automatically fills that geometry in and creates a solid body as a result, not two hollow bodies. Does that make, did I answer your question? I can go deeper into it if I didn't. I'm happy to delve down that path. Okay. So I didn't answer the question though. I prefer step because I have control over it. Where STLs, I have to jump through hoops to make it do stuff. If I can't get access to the CAD and I have to derive the CAD, because I almost never use STLs in my designs I mean, it's the output, but I don't use it as part of the design. And if I can't get the actual CAD, I'll use the STL and I'll generally re-CAD it based on that shape, so I have a solid body to work with in my CAD. Well, think of it, you know the difference between a bitmap and a vector graphic? A vector graphic defines a circle as the center's here and the radius is X. So when I draw that circle, no matter how close I get to it, that circle arc has no jaggies in it. When I draw a bitmap, I have a field of dots, and I poke dots into it to create a circle. And if my dot field is big enough, it looks like it's a smooth line. But if I zoom in, I got a bunch of dots. So STL, bunch of dots. CAD, a vector graphic, where it's defining the shape using math. So however close I get to it, however I zoom in and zoom out, that math is there for us to support the curve we're actually trying to create. So yes. Sure, but the analogy is you're still dealing with a non-calculated result. You're dealing with a preset result. That shape, however many triangles you put in it, you can put more triangles, because if I didn't have a lot of triangles, I wouldn't get a smooth STL out of it. But if I had a step file to start with, it's going to draw as smooth as that slicer is able to resolve based on your nozzle size and whatnot. Yes. So what else? Where do I post? That's a good question. So I started out way back when on Thingiverse, and so I started posting there. And then one day I got the polite invitation, Tim, would you like to host your mods on the OneDrive, Mr. Badley? And I was excited, yes. So I started posting them there, and I have access to a number of folders that most of the modifications I've done to Mr. Badley's work are on his OneDrive as living in the file structure. And then when I started building non-related stuff, I thought, I can't really post this. So I created a printables account, which is sort of like I don't know, it's like Thingiverse, but better. And so it is. So I've been posting, I have a printables account that I post stuff on there. I have a paid level on there that I think I have 2, maybe 3 subscribers, but because they make you. So most of the stuff I put up there, like the Arduino model, that's a premium model. It costs you $5. And then you can unsubscribe. But everything else I put up there for free. I'm not trying to make any money on this. I'm just trying to get stuff out there. And usually there's, I have a YouTube channel, which I had on there, which it's how I put stuff together. I'm not like, hey, like and subscribe. It's nope, here's how I built my whatever project it is. So I don't know. It's the Hebel, I think, or yeah. So if you go to my YouTube account, there's links to my Facebook builders page and my printables account. Yeah. What else?
Any good tips for like rapid iteration or things that have been
Well, what I've grown to learn is using the timeline in Fusion. I spent the last month or so designing a droid for the Autodesk Fusion contest to build a droid. And part of the design requirement was you had to show your timeline. Up to that point, I did Arduino, and I spent about a month and a half with the timeline. And then at some point, I'm like, this is too hard. I turned it off and threw it away. But since it was a design requirement, I went through and did the painful task of learning tools, tips, and techniques of using the timeline. And now my goal for the next few designs is to always use a timeline. And I'll do a quick, why do I want to use the timeline? This is kind of out of scope, but I think it's appropriate. If you will give me a second, I will pull up the project I'm talking about. Because the timeline ultimately is more powerful than direct modeling. Now, there's direct modeling is you extrude, you cut, you fill it, you chamfer, and you do all the things that make the shape you want. And there's a little kind of rabbit trail up and down the side of the screen that's moderately not useful. It just makes you scroll a lot. But at the end of the day, that shape. But if you need to go back and change anything to that shape, because, I need to use M4 bolts because the M3s are not weight-bearing enough or whatever, then you have to go back and recut every single one of those holes, and it's a big task. So if you're going fast, you can go without the timeline if your project doesn't have a lot of scale or scope. If you're doing something with lots of parts and lots of pieces, I always recommend using components for your major assemblies, because your components encapsulate everything about that, and then you can offload them to your project, and they become non-malleable, and you don't mess them up by accident. So use components, have several files on your hard drive, and import them into your master project. Is kind of my workflow. But let me bring up an example of timeline wizardry in why I think the timeline has a lot of use. And give me 1 second. Components is what I'm looking for. A, B, C, D, E, F, G. Why is this alphabet in that order that it's in? Is it because of that song? Stephen Wright? Nobody knows that joke? All right, so last week this guy was running Shadow, and he had a Arduino in it that was mounted back here. He had an MP3 trigger that was mounted here. And when I upgraded him to Kyber, he needed a new mount for the Kyber, but it had to use the same holes as my old mount because I didn't want to re-drill my electronics board. So to that end, I created this little application in Fusion. So I'll sit down here for a second so I can manipulate it. So you can see at the bottom I have a timeline where I inserted a bunch of components, and then I drew a bunch of pictures. And I have a bunch of extrudes, and a couple of fillets and chamfers, a bunch more pictures, and a line. So the secret sauce here is I'm using something called configurations. And the configurations brings up this little tab, and what it allows me to do is set variables. So when I drew that picture, I have hole X1, hole Y, hole X2. Then I have stud X1, stud Y, stud X2, and stud offset. So those parameters allow me to measure my board, measure the holes, and put those values in this table. And then when I pick a new component, it's going to run and redo the math for me for all those pieces. So bam. Now I have a T4 mount or a HCR vocalizer mount, and I didn't have to do any heavy. I can put any component, any 4 holes on my mounting plate, any 4 studs for mounting the board, and this will draw it for me using the timeline and parameters. So this is, and it even labels it. So when you pull it out, like, which one does this go to? So that's kind of the power of the timeline in a nutshell. Using the timeline is a whole other topic, but I'm glad that someone allowed me to launch this because this is neat. That's what rapid iteration, when you combine your tools to the point where you can use your own work as the basis of future work, that's kind of the secret sauce. Reusing components and modeling components. Anytime I'm building something that uses electronics or anything, I model it if I can't find the model already. So you can see this is my components folder, and you can see I got motors, I've got bearings, I got speakers, I got servos, and that not only makes your designs look cool, but it helps you avoid those pitfalls of you can't put the servo in because you didn't make the hole big enough type of thing. So that's kind of a wow. Anything else? All right. Well, thank you for your time. I appreciate the opportunity.